Imagine turning towering trees from vast American forests into the lumber that builds homes, skyscrapers, and entire cities. But have you ever wondered what happens between the forest and the final product? Today on Datascope, we're taking you inside one of America's giant timber factories to uncover the incredible journey of wood production. From massive logging operations and high-tech harvesting machines to powerful sawmills processing thousands of logs every day, you'll witness an industrial process operating on a truly astonishing scale. The speed, precision, and engineering behind this industry are enough to leave anyone amazed. Stay with us as we reveal how millions of tons of timber are transformed from raw trees into valuable building materials that shape the modern world. This is the incredible story of America's timber industry, and it starts right now on Datascope. In the United States, harvesting forests of tree species like pine, oak, and birch provides a plentiful supply of raw materials for paper production. The harvester is a highly versatile machine central to the wood harvesting process, equipped with specialized features. It can process up to 200 metric tons of wood per hour, achieving a record-breaking speed in the industry. While it can manage trees with a maximum diameter of 80 centimeters, it typically processes those ranging from 10 to 30 centimeters, which are optimal for paper manufacturing. Unlike the feller buncher, which only cuts and groups trees, the harvester excels at multitasking. The harvester integrates multiple operations like cutting, gripping, trimming branches, and segmenting trunks into a single streamlined process. Its advanced hydraulic system enables rapid movements, while automated sensors accurately identify trees and adjust operations accordingly. Equipped with high-efficiency blades, the cutting head minimizes waste and significantly boosts processing speed. Once the harvester completes its tasks, the forwarder efficiently collects and transports the processed logs out of the forest. Designed for rough terrain, the forwarder maintains stability and safety while carrying large volumes of timber without damaging the environment. This capability not only helps preserve the forest's ecological structure, but also ensures a continuous and reliable flow of raw material to paper mills and other wood processing industries. By serving this critical intermediary role, the forwarder keeps the entire logging operation running smoothly, allowing the industry to achieve massive production levels of up to 15 million tons of timber while minimizing negative impacts on forest ecosystems. In areas with steep or uneven terrain, skidders become the primary workhorses, stepping in to replace forwarders and ensuring that timber transport remains continuous and efficient. Equipped with powerful engines producing up to 700 horsepower and specialized systems, skidders are built to handle the harshest forest environments. This robust design allows them to operate reliably in muddy conditions, on steep slopes, and across rugged terrain where conventional vehicles cannot reach. Even the most remote logging sites can now be accessed and harvested safely and effectively. I immerse myself in the raw sounds of logging operations deep within the vast forests of the United States. Modern machines such as harvesters, forwarders, and skidders have triggered a complete revolution in the forestry industry. By replacing hand axes with mechanical power and advanced technology, logging has become a precise and highly efficient operational system. This transformation has led to unprecedented productivity levels, optimized costs, and an accelerated timber supply chain. After leaving the forest, I observe the massive logs gathered at the sawmill's log yard, stacked in long rows like giant stockpiles awaiting transformation. To maintain their quality, I notice that many mills spray water or submerge the logs in holding ponds to prevent cracks and protect them from mold. As the logs move to sorting, workers and laser scanners assess each trunk, identifying which species, measuring diameter, and checking for defects. Logs with the best characteristics are reserved for top-grade lumber, while those with imperfections are allocated for other uses where such flaws are less significant. Before reaching the saw blades, many logs pass through a debarking machine to remove the rough outer layer, which affects both the steel and the finish of the lumber. I applied debarking primarily to softwoods like pine, fir, or spruce, which are crucial for construction due to their consistency and stability. In smaller workshops or for handcrafted products, I sometimes saw logs directly and treat their surfaces later, occasionally leaving the bark on for a rustic appearance. Every tiny wood chip produced in this process is collected and utilized, reflecting my commitment to resourcefulness and sustainability. I use a laser scanner to capture every detail of the log's dimensions and imperfections, ensuring precision in the cutting process. The specialized software then generates a three-dimensional model and quickly determines the best cutting pattern to maximize usable wood while maintaining quality. Prepare the cutting map and move the log into a high-powered bandsaw based on the required cuts. I can choose between plain sawn cuts for high volume with sweeping grain patterns or quarter sawn cuts for greater stability and higher value. These methods require a balance between economic efficiency and long-term quality, as they yield different results in terms of output and labor. Once the method is selected, I begin to break down sawing with steel blades that slice the logs into larger slabs or semi-finished blocks. Finally, I open the log, separating its core from the outer sections, and stack the slabs on the conveyor while an automated system monitors the process. Blade speed, vibration, and the thickness of each cut are continuously monitored by sensors during the lumber transformation process. Amid the noise of steel cutting through wood, rough planks emerge from a log, marking the start of the lumber's journey. The slabs then move to the precision saw line, where they are resawed into boards of exact thickness for commercial use. This resawing process is highly precise, with sensors ensuring minimal margin of error for thickness variations. Finally, the boards undergo edging to trim irregular sides, resulting in clean, square edges that facilitate stacking and transportation. Observe that even discarded strips are repurposed into particle board, plywood, or biomass fuel. As the slabs become flat, straight-edged boards, I notice lumber stacked in seemingly endless rows. Technicians monitor operations on-site, performing random inspections to ensure every board meets exact specifications before progressing. I recognize that lumber retains a high level of natural moisture, which could lead to warping or cracking if untreated. To stabilize the structure, I see the boards are stacked with thin spacers for even drying in the kiln, where hot air is circulated by powerful fans. Temperatures during the drying process can vary significantly, reaching from 120 degrees Fahrenheit to over 210 degrees Fahrenheit, depending on the wood species and its intended use. I carefully regulate humidity within the chamber, initially drawing moisture out quickly and then slowing the process to ensure the core and surface dry in harmony. My goal is to achieve an ideal moisture content of about 15 to 19% for construction lumber and 6 to 8% for high-grade furniture, enhancing stability and reducing mold and insect issues. After drying and smoothing, I send the finished lumber to packaging, where automated systems stack the boards into organized bundles. I then use hydraulic arms and straps to secure the bundles tightly, creating solid blocks that can weigh several tons. To protect the wood during storage and transport, I often wrap the outer surfaces of each bundle in thick plastic sheeting or cover them with waterproof tarps, with some mills even using wooden frames for added safety. Each bundle is labeled with essential details like wood species, dimensions, production date, and destination for traceability and distribution. Once secured, I use forklifts to load the bundles onto trucks or into containers to prevent shifting or damage before reaching the final users. Meanwhile, the side streams, such as wood chips, offcuts, and sawdust, are collected and transformed into MDF, an engineered wood commonly used in buildings and furniture. The process starts with gathering scraps, cleaning them, and then grinding the material into fine wood fibers, which become the foundation of MDF. Begin with fibers entering a mixing chamber, where they are coated with urea, formaldehyde, or melamine urea formaldehyde resin to prepare them for binding. The fiber resin blend is then spread into a thick mat and lightly compressed before undergoing significant heat and pressure in the hot press stage. During this process, the resin liquefies and hardens, fusing millions of strands into a single board, marking the creation of MDF. After leaving the press, the panel is cooled and trimmed to precise dimensions before being sanded to achieve a smooth finish. Ultimately, MDF emerges as a stable and versatile material, maximizing the value of harvested trees and extending the utility of wood beyond traditional applications. From the moment a tree is harvested in the forest to the instant it emerges as precision-cut lumber, America's timber industry showcases an incredible blend of nature, technology, and industrial engineering. These massive factories process enormous volumes of wood every day, supplying the materials that help build homes, businesses, and infrastructure around the world. If you enjoyed this behind-the-scenes look at one of the world's most impressive wood production processes, be sure to like, subscribe, and turn on notifications so you never miss our next exploration of amazing factories, megaprojects, and engineering marvels. Thank you for watching Datascope, and we'll see you in the next video.